For the introduction of Poisson distribution, the Poisson distribution is a discrete distribution that measures the probability of a given number of events happening in a specified time period. So for examples of a Poisson distribution events are the number of the orders your firm receives tomorrow, the number of people who apply for a job tomorrow to your human resource division, and the number of defects in a finished product. Next, the three important facts about a Poisson distribution are: the standard deviation is always equal to the square root of the mean. The exact probability that a Poisson random variable x with mean is equal to a is given by the formula written, where e 2.71828 is a special number. If the mean is large, then the distribution is approximately normal.
The picture shows Simeon Denis Poisson, a French mathematician and physicist. He was born in Pithiviers, France in 1781. He went to the École Polytechnique to study physics and mathematics under the tutelage of the mathematicians Pierre Simon Laplace and Joseph Louis Lagrange. He was hired as an astronomer by the Bureau of Longitudes in 1808. Poisson passed away at Sceaux, France in 1840. The Copley Medal was presented to him after his passing in 1841. Poisson showed a profound impact on a variety of disciplines including physics, engineering, and mathematics. He published his research on the interaction between charges at a distance in 1809, demonstrating the idea of electricity and magnetism as well as in optics. Mathematics is the study of mechanics, electricity, and magnetism, and other branch of physics was the focus of Poisson's most significant work. For many years, his treatise on mechanics book, published between 1811 and 1833, served as the industry standard.
Applications of Poisson's in the field of business can offer the firm management information into operational efficiency levels and recommendations for methods to boost the productivity and enhance operations. Such example, the businesses use the Poisson's formula to determine if it is profitable to keep a store open 24 hours a day, and also checking for adequate staffing in the customer service department. So the image shown is the formula for the Poisson's distribution. Now, let us continue with the calculation of checking for adequate staffing in the customer service department. Let us use calls to support desk as an example. On average, a support desk receives 2 calls every 3 minutes. What is the likelihood of getting 4 fewer calls in a 9-minute period? So, assuming it roughly follows a Poisson process. Let x represent how many calls there are in a 9-minute span. B the average number of calls made during the specified time period is 6. So by knowing the average number of calls throughout the same time period, we can use the Poisson distribution function to compute the probability of 4 or less calls within the specified time period. So the image shown is the probability of receiving 4 or fewer calls within 9-minute period.
Next is about the application of Poisson in waiting time of an event. An interesting part of Poisson process involves figuring out how long we have to wait until the next event. This is sometimes called the interval time. The probability of waiting time can be specified by the amount of time between subsequent events decrease exponentially with the passing of time. To better comprehend how Poissons might be applied in the context of waiting time in real life, the following equation is about the probability of waiting more than specific time. Next, with our example, if one event per 12 minutes and if we plug in the numbers, it will get a 60.65% chance of waiting 6 minutes. It can be expected to wait more than 30 minutes about 8.2% of the time. This occurs between every subsequent set of occurrence because the interval between events have no memory. The gap between any occurrence has no effect on gap of time. A Poisson gives the probability of a number of events in interval generated by a Poisson process. The Poisson distribution can define the waiting time between events. Event it can be arrived at the random time. The average waiting time always be the average time between events.
Impacts on human's life. When it is known that individual event happened independently and at a constant mean rate over a given period, the Poisson distribution is used to predict the likelihood that a specific number of events will take place within that period. For the probability distribution of the number of y rare events that occur in space, time, volume, or any other dimension, the Poisson probability distribution frequently serves as a reasonable model. Here's are the example of the Poisson distribution in real life. Queuing theory makes use of a Poisson distribution specifically. In essence, the banking industry is where Poisson distribution is most used. It is typically used to calculate the likelihood of client bankruptcies in a specific period. For instance, if bank records reveal that on average 4 bankruptcies are filed each month in a certain region, this information can be used to project the likelihood that either 0, 1, 2, or 3 bankruptcies will be filed the following month. This aids bank management in calculating the amount of reserve cash that must be on hand if a predetermined number of bankruptcies take place.
Hello, I'm Ashraf from IS. I'm going to continue on the impact in Japan. Japan is earthquake prone. Quake forecasting is vital for the archipelago, hence much research is done on it. Due to the multiplicity of geological and physical components, predicting seismic activity will be difficult even in this century. The Poisson approach helped Japanese researchers investigate the country's regular seismic activity. They can research the Japan earthquake forecasting by utilizing Poisson distribution. From this, they can use it to predict earthquake in a certain period. They might be cautious to avoid the earthquake or be prepared for the worst. Impact in Tanzania. Automobile accidents are increasing in Tanzania. Accidents are harming life, property, the environment, and the economy. Tanzania road accidents and contributing factors were studied using Poisson regression. Poisson regression was introduced to evaluate the link between road accidents and their contributing factors, such as irresponsible driving, careless pedestrians, excessive speed, malfunctioning cars, motorcyclists, slippery roads, and poor visibility. All elements causing road accidents indicated a little increase in accident. Hence, the report advised the authorities to continue monitoring traffic control legislation. Then the impact in Malaysia. In Malaysia, a landslide can be one of the most damaging geohazards. The researcher decided to do landslide hazard mapping using a Poisson distribution and compare it to the earlier probabilistic approaches, such as frequency ratio, statistical index, and nominal susceptibility factor. They can determine the cause and ways to prevent the landslide based on this method. The likelihood comparison aids in preventing landslide in the constant state.